Hey. Good evening, everyone. Everyone here at the Stardome, everyone on YouTube. Welcome. My name is Chris Benton, and welcome to another Introduction to Astronomy session, where ideally I like to pick a topic in astronomy and use that as a vehicle to explain important principles of astronomy in general, and that's what I hope I do today as well. So don't forget online, guys, if you like the content, smash the like button and don't forget to subscribe. Okay, guys, so let's get underway. So this is probably familiar to a lot of you. It's the Hirschsprung-Russell diagram. And it's an important and a very powerful tool that astronomers use to plot stars. And you'll see here on the x-axis, that's the temperature, the surface temperature of a star or an object. It's in logarithmic, and it starts cold, the lower temperatures here at the down at the right-hand side, and then as you move more to the left, you get to higher temperatures. On the y-axis, you've got the luminosity, which means the brightness of a star. And it's another way of putting it, it's power output, it's energy that it's generating. And they use the unit they use is called the luminosity. And a lot of things in astronomy we relate back to the sun, one solar unit. And the big ones we tend to, three and most commonly used ones is one luminosity, one solar luminosity. That means the brightness or the luminosity of our sun. The other one will be, you'll see, solar masses, and that refers to the mass of the sun, which is about 2 times 10 to the 30, so it's 2 with 30 zeros after it, kilograms. That's one solar mass. And the other one you'll often do is for the size of a star, you relate it to the size of the sun. One solar radii is the radius of our sun. So that's just a bit of introduction there. So, and you'll see how some of the stars that they frequently plot here, they're down to, 1/10,000th of the brightness of our sun, and it goes right up to a million, sometimes more than a million, times the brightness of our sun. So if you think our sun's pretty bright on a hot day while you're sunburning, just think of those places. So anyway, that's your Hirschsprung-Russell diagram, and it so happens that if you get a whole big population of stars and you plot them according to their temperature and their brightness, you get a nice sort of series of patterns like this, or groups, if you will, of stars. They're not just higgledy-piggledy all over the place. And you'll see this big group up here going up diagonally up the graph. That's called the main sequence, and that's where stars spend the first 90% of their life in this state, on the main sequence, and it's a very stable state, and they're burning hydrogen to helium in their core. So that's the main sequence. I put our sun there. Everyone likes to know, where does the sun fit amongst that lot? Our sun is a main sequence star. Naturally, lining it up, it's at brightness at one luminosity for the reason we've just mentioned. And then its surface temperature is about 5,800 degrees. So the sun sits about there. You've also got groups of stars called giants, and that's when these sort of middle, sort of low to medium mass stars evolve off the main sequence. They turn into giants, and when these larger stars evolve off the main sequence to become supergiants. And then these things down here called white dwarfs, which are the end result of low to medium mass stars, stellar corpses. So that's the Hirschsprung-Russell diagram. These are the groups that we frequently talk about or hear people talk about. They talk about sort of low to intermediate mass main sequence stars. They talk about giants. They talk about white dwarfs. And that's often all people talk about. Yak, 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 yak. All they do is just want to talk about these groups of stars. So I thought something's got to change around here. So I thought we'd do a 2-part mini-series. Tonight is part 1 on massive stars, these groups of stars up here. And then part 2 next year, probably in March, because February we'll have our annual fun quiz, which will review all of this. So probably March we'll do part 2, which will be the infant stars of the galaxy. So I need a bit of time for audience participation. Can someone tell me the name of this object in the sky?
Orion.
Yeah, Orion Nebula, Great Orion Nebula, M42. How about this one here? Carina Nebula, absolutely. Well done, Neville. This object here, what nebula is this? Eagle, yep, Eagle Nebula, M16. And the clue, of course, is the pillars of creation here. And how about this one here? James W. recent image, one of the first James W.
The pillars of creation.
Yeah, they're called the cosmic cliffs. It's one of the James Webb first images, and it's just a small segment of the sky just up here, just off to one side of the Carina Nebula. So what have these things all got in common? The regions of star formation, absolutely. I should have had chocolate fish or something for this game, shouldn't we? Yeah. I would have eaten them all on the way down. So that's why tonight's talk is called Regions of Star Formation. It's part one, Home to Massive Stars. And I'm going to give you an introduction to these massive stars that people often don't talk about. You'll often see, or they're categorized, you see all these weird names they call them, and you think, whoa, where does all this fit in? So I want to give you an introduction to the principles behind these massive stars, some of the types of stars in the galaxy, so you can fit it all together and explain to you why they're usually always found in regions of star formation. So I've split it up into three sections. First one, we'll be talking about 6 principles of massive stars, which applies to general astronomy. We'll then talk about the different types of massive stars. There's 6 main types. We'll go through those, the different types, and we'll talk about some examples of them as well, examples of stars that you can see yourself. And then we'll talk about the groups in which you tend to see these massive stars, usually in open star clusters or associations, and they're all located in regions of star formation. So, 6 principles of massive stars. Let's have a look at them. So we're going to talk about their masses, how they're all more than 8 solar masses, how they're all highly luminous, which you now know means highly bright, very, very bright. We're going to talk about how they've all, in their cores, have really high temperatures, how they have a very effective methods of transferring that high energy, that heat from their cores out to the surface, how and why they're relatively rare, and why they are also very unstable, their surfaces, with associated loss of their mass. And that's really one of the main things that drives the whole evolution of the different types of massive stars. Okay, so massive stars all have mass or amount of stuff or matter in them greater than 8 solar masses. Let's just have a look here. So this diagram is quite a good one just to review how stars live, how stars evolve, and how stars die. And you really tend to split stars into 2. Those less than 8 solar masses, these are called low to medium dwarfs. I should mention here, any star on the main sequence is labelled a dwarf. There's only 2 types of stars. When you think of stars, what are the different types of stars? There's only 2 types. Dwarfs, most of them sit on the main sequence, then you've got your white dwarfs and your brown dwarfs and black dwarfs, but essentially anything on the main sequence is labelled a dwarf. Doesn't matter how big it is, it's just called a dwarf. And you've got giants, your red giants and your red supergiants and so on. So that's how you generally classify stars. So you've got your main sequence, low to medium mass dwarfs. All good things come to an end, so they sit on the main sequence burning hydrogen into helium at their core, nice stable state where they spend 90% of their life. All things come to an end and they eventually run out of hydrogen in their core. What happens then? They start burning hydrogen in a shell around the core. That causes the star to swell up. In this case, it turns into a red giant. That's the sort of state where it'll spend the next 10% of its life before all its outer layers generally puff out to form this beautiful planetary nebula and then to become a white dwarf. Massive stars are considered those stars greater than 8 solar masses. Why? Because these are the stars that all end in a big supernova explosion. So here they are, they do the same, 90% of their time are sitting on the main sequence burning hydrogen to helium. They then run out of hydrogen at their core, so they start burning shells around the core. That causes it to swell up, but you've got so much more mass and energy and heat going on in there, which we'll talk about shortly, that they become red supergiants. They all go boof into a big supernova explosion. If they're between 8 and 20 solar masses or thereabouts, they usually end up as a neutron star for their stellar corpse, or greater than 20 solar masses, a black hole. So that just puts it all in perspective, what we mean by massive stars and how you tend to split the two up and where we're heading with it. So here is your main sequence. So point number 2, again, is massive stars all have a wide range of temperature and are all highly luminous. They're all bright. So here is your Hertzsprung-Russell diagram. Here is your main sequence running up full of all your dwarfs. And I've circled here, here's your cutoff point, about 8 solar masses is roughly about there. And I've circled it all here. So all these stars here are all called massive stars. As you can see, there's a wide range of temperatures. They're up to, surface temperatures of 50,000 degrees, right down to surface temperatures of about 3,000 degrees. So a wide range of temperatures. But what have they got in common? They are all extremely bright, highly luminous, so they're all based up at this end of the Hertzsprung-Russell diagram. What determines their luminosity, or how bright are they? And there's two main things. It's a star's temperature and its size. Very simple, basic formula in astronomy. The luminosity, or the power output of a star, is dependent upon 2 factors. Here's the formula. 4 times pi, you know what pi is, 3.14, carry on. Sigma is just a constant, a Stefan Boltzmann constant that's commonly used in astrophysics. But the 2 variables here is temperature to the power of 4. So the temperature of a star plays a huge role in how bright it is, and then the square of its radius. So the bottom line, it comes down to hot stars and large stars are bright. That's the bottom line. And that's why they're all very, very bright. They're either hot or they're large. Sometimes both. Okay, principle number 3. Massive stars have high core temperatures via the CNO cycle of hydrogen nuclear fusion. What does all that mean? Okay, so stars, as we mentioned, spend 90% of their lives on that main sequence burning hydrogen to helium in their core. There's 2 ways they can do that. One is the proton-proton chain, which is a series of reactions involving nuclear decay, and that produces sort of so much energy per temperature. And the other one is the CNO cycle, and it's a cycle whereby, with involving nuclear fusion, whereby carbon, nitrogen, oxygen are used as catalysts. So they go into the equation, they come back out again as carbon, nitrogen, oxygen, but it's able to convert protons or helium, hydrogen nuclei into helium. So how does this apply to what we're talking about? So you'll see on this graph here, well, first of all, a little principle that we're going on here. Let's come down to here, some basic principles. A bigger a star is, or the more massive it is, it's got more gravity because of the mass, so more gravity is pushing inward on it, which creates higher pressures and temperatures at the core of that star. That's important. And stars up to about 1.5 solar masses. So this graph here, along the bottom you've got temperatures of stars here, and I've drawn a line here at 1.5, here it is here, and that equates to about 18 million degrees. Up to about 18 million degrees, in other words, any star less than about 1.5 solar masses, the proton-proton pump is the predominant method of burning hydrogen to helium at the core. Over 1.5 solar mass, you've reached a critical amount of matter, you've reached a critical temperature where you suddenly get past that barrier of about 18 million degrees at its core, and suddenly, as you can see here, the CNO cycle becomes the predominant method of fusing hydrogen to helium. The other thing you'll notice here, on the y-axis, this is the energy generated by these processes. And as you can see, the proton-proton pump generates sort of yay amount of energy, then it sort of tapers off as the temperature of the core goes up. But the CNO cycle is really sensitive to the temperature of that core. whereby as the temperature goes up, you can see, look at the energy output, just starts rocketing upwards. And so massive stars all have core temperatures greater than 18 million degrees. They're all well and truly, as you know, we've just talked about that, they're actually 8 and over solar masses, but anything over 1.5, and you've got the CNO cycle. So your 8 is probably up here. It's not clear on this where it is, but let's just say it's up here, for example. You can see it's way up here. It's producing much more energy than these stars way down here. Point number 4, massive dwarf stars have effective inner convection zones of heat transfer. The two main forms of transferring heat from this really hot core where the CNO cycle is just blazing away, creating huge amounts of energy. So how do you want to get that energy and heat out to the surface most effective way that you possibly can? And stars like our sun, from 0.5 to 1.5 solar masses, they have, oh bless you, they have an inner radiative zone and an outer convection zone. In other words, photons of light travel out through the inner zones of the star, outside the core, but within the content, the rest of the content of the star. The inner part of that is radiation, so just photons bouncing around, and then eventually it gets to convection. And that's okay, but it's not totally efficient. A far more effective way is what massive stars do. They have an inner zone of convection, which is very, very effective, out to a certain point out, and then radiation kicks in and the photons can go out a lot more freer out to the surface. Very effective. Now you might say, well, why is that so? Who organised this? And it all comes down to this, what determines whether you're going to do convection or radiation? It depends on the conditions within the star, whereby a very steep temperature gradient will favour convection, and the transparency or opacity of ultraviolet light in the environment of hydrogen within the stars determines with its radiation. So in these massive stars, you've got these huge energy input, or output I should say, coming from the CNO cycle, whereby you've got a massive temperature gradient going on just outside the core. So that favours convection. It gets to a point where the temperature gradient drops off and you no longer get convection, but meanwhile, the temperatures in the outer regions of the star are still hot enough for the hydrogen to be ionized, which allows the photons, and particularly ultraviolet photons, just to zip right through. And so that's a very, very most effective way of transferring the heat from these really hot cores, generating huge amounts of energy with a CNO cycle, get it out to the surface to create a really hot, highly luminous, powerful star.
Chris, does that mean the photons get out faster than they do compared to our sun?
Yes, yes, they do. Yep. The key to it is having that convection right up outside the core, and it's just the conditions in our sun whereby because we were talking about it earlier on. In our sun, just a little nice little sort of little side thing. The photons from the core of our sun, they leave as gamma rays. And as they zip through here, through the radiative zone, it takes about 170,000 years for a photon to get from the core to this part here, about anywhere between 3 and 5 days with convection to get here, and then 8 minutes to zoom to Earth. So that's, so this pretty much summarised what we've really gone over here. Stars over 1.5 solar masses, higher core temperatures from the CNO cycle, higher inner zone gradient, inner zone of convection, and then the ionized hydrogen allows ultraviolet light to zip through it, and the outer radiation. So that pretty much we've covered. Okay, principle number 5. Massive stars are relatively rare, so you don't see too much of them. Why is that so? I want to take a step back at this time and just talk another little principle of astronomy, is that astronomers class or classify stars by, they call it the spectral class. And what do we mean by spectral class? Examining a star's spectrum refers to astronomers will get an instrument and they'll put a prism or some grating in it, and that splits the light up from the star into all its various wavelengths. Much like light from the sun gets split by raindrops in the middle of a misty sort of rain, gets split and you create rainbows. Exactly the same principle. So when they split the light of a star into all the various wavelengths, they get a lot of information from that. They can tell the temperature of a surface, they can tell what atoms and elements are in and around that star or object. They can tell whether there's a movement of material or the object itself towards you or away from you. You get an idea of the velocity. There's a powerful lot of information if you start splitting up light into its various wavelengths. So astronomers do that. They get the light from stars and they split it up and they classify them. And you start off, this is not to scale, by the way, guys, but this just gives you an idea here. You get the general theme of it. Hot and large stars up here, they're labelled O stars, spectral class O. Then you go spectral class B, and slowly the stars getting smaller and cooler and dimmer. Not to scale, but you get the idea. Hot, large and bright stars go down to cool, small and dim, and these are M. Now you might say, well, by the way, here's the sun. Sun's a G class. You might say, when I went to school, the alphabet went something like A, B, C, D, E, F, and G, something like that. What's going on here? Which school did these guys go to? They started classifying them originally, historically, by the amount of hydrogen emission they saw in the stars. And they didn't understand stars properly. They thought, where do we start? Fair enough question. Let's start with hydrogen. So that's how they classified. They did have A, B, C, D, but of course we learnt more about stars and about their luminosity and brightness. And when you line them all up, it makes more sense to line them up in this fashion, but they kept the letters the same. So that's how they do it. So essentially it's determined their surface temperature and the size of the star determines its spectral class. Just another little comment down here is that the classes are then broken into subclasses. So for example, G's are then split into O through to 9 and so on, GO, G1, 2, 3. The 0 is at the hot end and it goes 1, 2, 3, 4, 5, 6, 8, 9, right through to the cooler 9 at the cooler end. And you think, oh, you might think of the spirit mode. How do I remember that? I just remember O or 0, O for hot, H-O-T, with the big O in the middle of it. That's how I remember it anyway, but you can remember it how you like. So, okay, out of all of these, so you might say, well, where are you heading with this conversation? I came to hear about massive stars. Well, massive stars, all the O class are all massive stars, greater than 8 solar masses. We're talking main sequence here, by the way. And some of the B classes. So it's the B0, B1 and B2 that are all tend to be more than 8 solar masses. So your B3s and your B4s and anything down that way to the left of this are going to be generally less than 8 solar masses. So that's a little bit about spectra, how they classify stars. And that's relevant for this slide here. Is that, yeah, nature has a bias for formation of smaller stars. There's far more small stars than there are large stars. And look, here's the M class here, well, these are the most smallest and dimmest. Look, they make up 76.5% of all stars, to the extreme whereby your O class make up 0.00003% of all stars on the main sequence. Hardly worth mentioning. The B class stars, 0.13%. So very little, of course, out of those B, you're going to split them up into 0, 1, 2, 3. And of course, what do you know is that there's going to be far less zeros and ones and twos than there are 3, 4, 5, 6, 7, 8, 9, and so on. So the bottom line is massive hot O and B dwarfs make up less than 1% of all main sequence stars. It's amazing, isn't it? So that's and the reason you might say, why is that? So why does nature have a bias for smaller stars? Stars form and tend to form in groups, as we'll see later on, from usually a giant molecular cloud that starts to become unstable and fragment into smaller and smaller fragments, and eventually the smaller fragments start collapsing to form individual stars. And it just makes sense. Larger fragments are more likely to split up into smaller and smaller fragments than, say, a smaller fragment that might just sit at that level, thank you very much. So it just follows that a larger fragment is more unstable. I put this one in here, so that's one reason why they're rare, is because there's not many of them made, but also another thing that makes them very scarce is they don't live very long. And I put this table in here, and this just refers to main sequence stars. And here's one solar mass, so that's our sun here. Our sun spends will spend about 12,000 million years on the main sequence, which is about 12 billion years, of course. But look at these massive stars here. So you've got 25 and 15 solar masses here. Look at them. The 25 solar masses, they're only going to spend 4 million years on the main sequence, a measly amount of time compared with the smaller stars. So look at the M-class stars, 700,000, which is 700 billion years on the main sequence. So they spend a lot. And you might say, well, why do they have such short lives? The reason being, as we've really discussed in a roundabout sort of way, the more mass, the more inward force from gravity, the higher pressures and temperatures, CNO cycle nuclear fusion going on, very, very effective, very temperature sensitive. They start pouring out energy. So what do you do when you're pouring out more and more energy? You're using up more and more fuel. So they just burn through their fuel so much quicker because of their big mass and inward force of gravity. So the lifespan of an average O-class main sequence star is 3,000 times less than that of our sun. Check that out. So that also goes to explain their location. Why are they very close to within and very close to regions of star formation? They don't have time to go anywhere else. So that's the reason why. They hardly have time to leave the nest. Pity that didn't happen to teenagers sometimes. Okay, point number 6. Massive stars have very unstable outer layers. And let's just talk about their principles, which we've just talked about. Due to their high temperatures and burning through nuclear fusion, and remember they got very effective at pouring that heat out through convection, and then the outer layers are pushing it out with radiation, just photons heading straight out. They have very high, what they call radiation pressure on their surfaces. That's the pressure of that photon radiation just pouring out. There's that, and because they have large diameters, they have low surface gravity, meaning the force that's holding you down on something. And to give you an idea, as I've written the formula up, their force is proportional to 1 over the radius square, the inverse of the radius square. So, for example, if you were, say, sitting on the surface of a planet yay big, and with yay x, sort of say, amount of surface gravity, if you double the size of that planet, but keep the same mass, of course, but you double the size of the planet, the force holding you down on that surface is going to be 1/4 the amount so the surface gravity holding you down is only going to be 1/4. If you were to triple the size of that planet, but keep the mass the same, the surface gravity would be only 1/9. So as something gets bigger, the amount of gravity holding it down to the surface gravity, gets significantly less and less. So high radiation pressure, low surface gravity equals strong stellar winds, a lot of winds just pouring out of those stars, and what happens? All the mass just gets carried, and a lot of mass loss goes on as well in these stars. And you can see it here in this GIF file. There's just mass pouring out of it because of these really intense winds that are going on. So that's sort of some key principles of massive stars and general astronomy principles as well. Let's now talk about the different types of massive stars with some well-known examples. This is a lot of information we're about to do to take on board, so for that reason, that's why you got your handout, so you can read it later on. I've got my email address later on. Anyone online can email me if you wish to copy of it. It's a 7-page job, and there's 1 or 2 other people who just came a little bit late. There's a pile of them here. You're well, help yourself. So also, I'm going to go over them and have a flow diagram afterwards and try and bring it together. So types of massive stars. So I'm going to give you a bit of introduction to the different types and what drives their evolution. We'll then talk about the classes O and B, these dwarfs on the main sequence. We're going to talk about the supergiants, blue supergiants, yellow supergiants, red supergiants. Then we're going to talk about Wolf-Rayet stars, luminous blue variables, and we'll briefly mention hypergiants. As I've mentioned here, we're going to talk about all the different types, and we're going to give you examples that you'll be able to see in the sky. And then I'm going to give you a flow diagram, which I hope will bring it all together for you. I was working on this flow diagram till 6 p.m. and I suddenly realized I had to grab some dinner and put some clothes on and get out the door and get here. So it's a little bit different. It's been modified to the one in the handout. So let's talk about introduction and evolutionary stages of massive stars. Okay, so in principle, we talked about this principle, how main sequence, and I might repeat myself, but it's just, I can't emphasize enough. Stars spend 90% of their life in a stable state fusing hydrogen. They then run out of hydrogen in their core, they start in shells around the core, start burning in the small, the lower to intermediate, they start burning just some hydrogen and then some helium, but it causes them to puff out and become these big red giants. And you might say, why do they get this red color to them? Well, if you get something of a certain temperature and you expand it out in size, you're still generating the same amount of energy on the inside, but suddenly your surface area, which it gets spread around, is suddenly increased significantly. So that surface temperature drops. And with it, the colour drops as well to a red. And the colours of the stars are just like flames, like your gas and all your flames in your fireplace. You know, you get your kindling going and it glows a little bit red and it gets a bit oranger, and throw some more stuff on it. And as the flames get hotter and hotter, you'd probably notice it more in your barbecue, for example. You start noticing the flames get a bit blue and whitish and so on. Same principle here. So yeah, massive stars are a little bit different, and that for reasons beyond the scope of this talk, we'll talk about it next year with stellar evolution, but needless to say, instead of just one or two shells, they get a multiple of various shells, like an onion, multiple shells of heavier and heavier elements. They start getting hydrogen, helium shells, carbon shells, nitrogen, oxygen, silicon, and then they get a core of iron. That's a whole different talk, but needless to say, they get a series of shells, and each shell is burning at higher and higher temperatures, and that makes the star really swell. The stars swell, plus, really swell up to become these supergiants. So my main thing is here, they start to swell up, and that makes them to get much cooler and brighter. Remember, there was two things that caused luminosity or brightness. There was how big, the size of something. So if something gets bigger, it gets brighter. And if something gets hotter, it gets brighter. And the second little comment here is that stars that will be driving this, which you're going to see, this is the main points of evolution of massive stars. They also can later start shedding mass away and start getting smaller, but you're starting to expose those hotter regions on the inside, so they start getting hotter and brighter from just being sheer hot, high temperatures. So those are two key points that drive the evolution of these massive stars and create these different types that we're going to get. Okay, so let's talk about our first group. Spectral classes O through to B2, these dwarfs on the main sequence. Here's our, here they are here, and they've got a white hue, and you might think, well, why aren't they sort of more a bluish colour? They are hot, and you'd expect them to be blue, but most of the light emitted by these big O stars is actually in the ultraviolet wavelengths, which means what we see visual-wise has got more of a white hue to it than a blue, so they sort of appear sort of more sort of whitish than blue. Here's your Hirschsprung Russell diagram, your main sequence, and here all these guys are up here, from about 8 solar masses, and you can see they go up to about, this diagram here goes up to about sort of 150 or so, though it is logarithmic. So they go way up here, sort of, I'd say probably even getting up to 200 on this diagram. So what is their range of temperatures? You can see a bit of a range of temperatures. Well, your B dwarfs down here, your mass is sort of about 8 to 16. This is going a little bit slow, that's cool. Temperatures down to about 20,000 degrees Kelvin, which is similar. You don't need to worry about Kelvin and Celsius and when you're getting to these levels. So about 20,000 degrees. Luminosity of those B2, these sort of the lower end of the massive stars, you're talking about a luminosity of about 3,000 times as bright as our sun. The O dwarfs, you can actually get up to 300 solar masses, which we'll talk about later. The surface temperatures get up to about 50,000 degrees, and you're looking up to a million, even up to 10 million luminosities. Imagine that, 10 million times as bright as our sun. So that's the sort of range of these stars, these main sequence stars, massive stars. So where can you see some of these in the sky? So this is Orion, and the trapezium cluster in M2 that we had earlier on. That was that very first area of star formation. So here's the constellation of Orion. And of course, if you're in the northern hemisphere, you'll see that as Orion's belt, and there's a sword hanging downwards. But we're here in the southern hemisphere, yay, 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 where we get far better skies. So we see this as a pot here, and here's the handle of it here. The middle star or point of light in that handle of the pot is the trapezium cluster, and it's a little open cluster of really bright stars sitting bang in the middle there of M42. And two of the stars in there, or two of the points of light in there, I should say, are main sequence massive stars. You've got Theta Orionis C here, which is this point here. That's the brightest star in the cluster. It's a binary system, and it's actually two massive stars in a binary system. One's an O6 main sequence one, and the other one's a B0 main sequence binary system. This one here, Theta Orionis, the D star, is a B1.5 main sequence star. So there's two stars, or three stars, you really could, strictly speaking, say, just sitting right there in the trapezium cluster that are main sequence massive stars. So it's rising in the sky in the evening's beautiful at the moment, so you can go out there tonight, point out to someone, point that middle light out, point of light in the handle of the pot, and tell them there are three main sequence massive stars up there, and they should be impressed. Okay, so let's move on. So what happens then is when these main sequence stars, they eventually run out of hydrogen in their core, so you start getting hydrogen shell of nuclear fusion around the outside of them, and then you get helium and so on. And during this process, the star starts to swell out a little bit. And what happens when the stars start to swell out? Their temperatures drop a little bit, and they start getting larger, so they're getting more luminous, getting cooler and more luminous. And here's your Hirschsprung-Russell diagram. Here, these main sequence stars evolving off the main sequence become blue supergiants. And here they are, so they're a little bit cooler, but also they get a little bit brighter for each relevant tract. Here it is, the temperatures range anywhere between 10,000 and 50,000, so there's quite a wide range of temperatures, depending where they are and in terms of how big they are and where they are along their state of evolution. And their luminosities up to 1 million times that of the sun. As we talked about, stellar winds, all these guys have stellar winds. These tend to have very sparse but very fast stellar winds. And their spectra, which we spoke about, is, remember, splitting the light into its different wavelengths, tends to give very broad emission lines. So emission lines means you've got an atom there that's emitting energy, light that you're picking up in your wavelengths. And they come in like little peaks. And when you see the peak, the emission peak broadening, it means it's splaying out. And that tells you there's a lot of motion going on, because something coming towards you fast, the line gets moved towards you or blue shifted. Actually, it goes the opposite way when you're thinking, depending which way you're looking at it, but it goes in one direction. And if material's going away from you, perhaps as the star's rotating around, but you've got high winds, it's going to be going the opposite direction. So the emission lines splay out, what they call broad emission lines. And that tells you that some very fast winds going on there. And they have a varying array of heavy elements in there. You've got your hydrogen, you've got your helium, and you've got some carbon and nitrogen and oxygen. You might say, well, how does that get there? You know, all that convection tuning up from all the contents from the core comes up through there. So that's a little bit about blue supergiants. What happens to them next varies accordingly to their mass. And here are some key principles coming up again. Anything up to about 40 solar masses, they're reasonably stable. They're still blowing off winds, but they're reasonably stable where they don't blow off too much mass, and they're allowed to continue to swell a little bit more and more and more. And they eventually go on to form red supergiants. And there's a stage which we'll talk about briefly called yellow supergiants in an intermediary phase. So they they hang on to most of the material, and they just gently swell out to become red supergiants. Blue supergiants, more than 40 solar masses, they are that little bit more unstable because their radiation pressures is higher, because they're higher temperatures. Their surface gravity is less because they're just larger in diameter. So they're more unstable. And they can lose mass in any way of two ways. They can lose it by a steady loss, just constant steady loss of material. They end up as Wolf-Rayet stars, which we'll talk about shortly. And we're going to go through this with a flow diagram, bring all this together later on too. Or they can lose mass sort of episodically in just an unpredictable, big, dramatic, sudden burst of material. And they create what they call luminous blue variables, which we will talk about. So that's here. Blue supergiants, what happens to them depends on their mass. Can anyone name a well-known blue supergiant in the constellation of Orion? Yes. You're onto it, Neville. Cool, yeah. Rigel. So here it is here. So here, once again, is your pot. And your handle of your pot, trapezium in there with 3 main sequence massive stars. And here is Rigel sitting right up here. It's a beautiful blue colour. It's shining very, very brightly. And just give you some figures here. It's about 18 solar masses. So what does that tell you? It's going to be much less than 40, isn't it? So what's that going to end up one day? It's going to end up as a red supergiant. It's going to hold itself together reasonably stable because it's less than the magic number of about 40. Radius-wise, it's 80 times the size of our sun. Temperature-wise, it's about 11,000 degrees. So that's Rigel. That is a blue supergiant. These yellow supergiants, which we spoke about, as I mentioned, a more intermediate phase, a very, very short phase. And what that is, it's these blue supergiants slowly swelling out to become red supergiants. And they sit here. It's a very, very short phase, just a few thousand years or so. So that makes them even more rare. Of interest, you've got what we call your instability strip. It's a strip that runs through here, the Hurst-Russell diagram, whereby the stars, and once again, we'll go into this next year when we talk about stellar evolution, but needless to say, they pulsate. And there's a class of pulsating stars called Cepheid variables. And they're really important because their rate or the period or the frequency, if you will, of their pulsating correlates directly with their absolute brightness, how bright they are. And astronomers use that as a tool for measuring distances. You can go and look up our talk. We spoke with a bit of detail how they do measure distances using Cepheids. That was earlier this year during lockdown. The online talks would have been about March or April or something like that. I did a whole talk on measuring distances, which we talked about Cepheid variables. So that's where your Cepheid variables sit. And so yellow supergiants, a lot of them are Cepheid variables. Their temperatures range from about 4,000 through to 7,000. Those of you wondering about the spectral classes, they're generally G and K. And their luminosities are very similar to the blue supergiants, to about 10,000 to, about 100,000 through to about 1 million luminosities, solar luminosities. Can anyone name a yellow supergiant? In particular, there's a famous one in the Northern Hemisphere that's a yellow supergiant. We won't see it from here. No, not Capella. Good day. I'll give you a clue. It's a very, 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 very famous star in the Northern Hemisphere. Polaris, yeah, the North Star. Who wrote a song called The North Star? 1992. It was an outtake from the album The One. Elton John. Go look it up. It was an outtake from the album. Brilliant song called The North Star. Got to throw that in there. Okay, so that's a yellow supergiant. So next time someone, if you're watching the movies and stuff like that, they'll often have a picture of the North Star or something up there. It sits right at the north celestial pole. So that's a yellow supergiant. I didn't know that till about 2 days ago. So then you move on, you get these red supergiants, which are really, really big and swollen. These are the largest stars in the galaxy, these red supergiants, and also red hypergiants. And you'll see later on, the word hypergiant just means really big supergiant. That sort of blurs into one. But it's this class of stars that this evolutionary stage is probably a more accurate way of putting it, are the largest stars in the galaxies. So these are from the blue supergiants between about 10 and 40 solar masses that have remained stable enough and have just gently swollen more and more and more out till they get to this size. Their temperatures are down into the K and M classes, so about 3,000 to 4,000 degrees. Here, this is where their radius is, the size of them. They can get thousands of times larger than our sun, whereby if you plonked one of them, and I won't give you the name in a minute, we'll talk about it shortly as an example. One of these guys, if you put it where the sun is, it will extend out to the orbit of Jupiter. Check that out. If you put it in the middle of our solar system, it would extend out to the orbit of Jupiter, We'll talk more about that. And the luminosity, they're actually, you can see here on the Hesperus-Russell diagram, they're a little bit brighter than the blue supergiants. Why? Because of their increased size. So their core fusion, they're burning through their helium. At this stage, when you start running out of hydrogen, you start getting in the core, you start getting a shell of hydrogen out the outside. The inner parts of the star can start collapsing down a little bit, and the pressures and temperatures in the core of that star rise even higher and higher and higher, till it gets to the point where the helium that's sitting in the core now, from the hydrogen fusion, starts burning away. And that's usually when it gets up to about 100 million degrees. And so it gets up to there, and the red giants, or supergiants I should say, are burning helium at this stage. Helium fusion kicks in either just before or at the red supergiant phase. And naturally that's at a very big high rate, so they took about 1 to 2 million years to burn. Their maximum lifespan, when you see one of these things, the absolute maximum lifespan is only about 25 million years, so they don't live very long. I wanted to talk about the concept of blue loops. This is an interesting little concept for evolution. And you'll see this term, you start picking up a book or a paper on red supergiants, and you talk about blue loops, and you think, what's a blue loop? Well, all it is that if the helium core in a star, in relation to its overall mass, is above a critical amount, the star gets really, really hot, and it starts shedding off its outer layers. Becomes a bit unstable. So as it sheds out its outer layers, you're starting to expose the inner hot parts of the star. So the star starts getting hotter and hotter, and of course it's starting to go bluer, more blue again, and it goes back into a blue supergiant. So increased mass loss because the helium core is just that much bigger, generating more energy, and it goes back through to a yellow supergiant and a blue supergiant. So here's your red supergiant stage here. It'll actually start backing track again to here to a blue giant stage. Then it stops there and starts swelling and goes back again to become a red supergiant. And that process is called a blue loop. So if you see that, it's just a really large red supergiant. It's got a little bit unstable, big massive helium core blazing away in there that's made it a bit unstable, goes back to blue supergiant, and then loops around and comes back to red supergiant phase. Can anyone, that's very visible in our sky, tell me a supergiant that's going through the blue loop right now as we talk? A clue, it's in the constellation Carina. Alpha Carina? Alpha Carina? Canopus. Canopus, Alpha Carina. So Canopus, which you often, because how many times you look in the night sky, and you look up and you think, oh, now you haven't got your phone on you, something like that. You're just trying to, oh, there's the first bright star up there. What's that? And just orientating yourself. You think, oh, okay, that's Canopus. You know, I often find Canopus first when I'm looking at the sky to orientate myself, just by chance. So when you look at that, that's going through a blue loop. That's a blue loop supergiant. So you've got to be able to tell someone that. If you've got any friends left at this stage. Can anyone name a well-known red supergiant in Orion that I was alluding to before that would go out to Jupiter? Beetlejuice, yay! Yeah, so here it is here. So here's your pot again. There's your handle. There's your three main sequence massive stars in there. Your blue supergiant Rigel here, and there's Beetlejuice here. That's a red supergiant. That's visible in the New Zealand summer. It's about 11 solar masses, so that's why it's reasonably stable. It's 3.5 surface temperature, 3,500 degrees Kelvin, and yeah, it's 887 solar radii. And if you put Beetlejuice in the middle of our solar system, it would go out to the orbit of Jupiter. The other one, which we see in wintertime, is Antares, in the constellation Scorpius. So here's Scorpius here, here's the head of the Scorpius, the heart, and the body here, and there's the tail there as well. So yeah, so Scorpius is very visible in our winter skies, and the big red spot in here, Antares, that's a red supergiant as well. Those are the two real prominent, well-known red supergiants visible to us. Look at this. Let's put these into perspective. So here's your Beetlejuice, here's your Antares, here's our sun down here. So here's our sun. Here's Rigel, blue supergiant that hasn't yet puffed out to a red giant. Arcturus and Aldebaran are red giants. So here's Rigel, but look at Antares and Beetlejuice compared with our sun. Crazy, isn't it? Yes, that's. I believe that is. You know what? Actually, I really doubt that. Yeah.
And the standard pixel is...
Yeah, it's a pixel. Yeah. It's just such a scale. Yeah. But the bottom line is to probably put it more in scale. Go out to Jupiter. Yeah. And I think they probably couldn't get, as Niven said, they've just given the sun a token pixel probably more than anything, so you could see it. Yeah. So there's only allowed one pixel, they've given it one. Yeah. Now let's move on to Wolf-Rayet stars. You'll often hear about those and you think, what on earth is a Wolf-Rayet stars? And the bottom line is, these are stars that evolve from main sequence stars, blue main sequence or red main sequence. And it's whereby you get one of those three groups of stars that has just continued to blow so much of its outer layers out, it's shed all of its hydrogen. Hydrogen tends to be the outer layers of a star. All the hydrogen has been completely shed off. If you just left the rest of the star exposed, and that is a Wolf-Rayet star. They're the hottest and brightest stars in the galaxies. No surprise, they've got extremely strong stellar winds. That's how they got into that state. Depleted hydrogen, and so when you look at them in the spectrum and you start splitting up all those different wavelengths, you see those broad emission lines again, because you've got a lot of material getting thrown out in these big, fast, ferocious winds, and you're getting ionized helium. You don't get no more hydrogen, and that's how you know. You're looking at the spectrum of this really hot star. So you've identified the star, and you've checked out measured its luminosity and its temperature. You've calculated, and you think, whoa, that sits way over here. You then analyse its light, and you see, well, it's got there's no hydrogen there. It's got prominent helium lines, and they're really broadened out, and it's either got some nitrogen, carbon, or oxygen there. And that tells you, okay, I'm dealing with a Wolf-Rayet star. It's been so ferocious, it's got rid of all its outer layers. They'll often have, as this one here too, they have an associated what they call a wind nebula, and that's just ejected material that's been all cast off from it, and it's just all hanging around in a nebula type situation. There are two types of Wolf-Rayet stars, your classical Wolf-Rayet stars and your WNH stars. Let's have a closer look at those, because that's very important. Your classical Wolf-Rayet stars are when you primarily, there's three ways you can get it. Primarily, it's from a blue main sequence greater than 40 solar masses. Remember, less than that, and it remains stable and swells out to a red supergiant. But this is more than that, and it just loses its materials in a continuous fashion to expose it. And that's the most commonest way you get yourself a Wolf-Rayet star. Less likely, you can get a extreme mass main sequence O dwarf that just as it leaves the main sequence, instead of going off to a blue supergiant, it just starts shredding all its material so quickly, it just turns straight into a Wolf-Rayet star. And you can get red supergiants that become unstable. We mentioned the blue loops. You get some of the bigger ones that can shed all their material off. They're just so unstable. That helium core really is quite large compared with the rest of the star, and they end up as Wolf-Rayet stars. So how about your WNH stars? These are where you get really, really extremely large main sequence stars. They shed all their outer layers of hydrogen while they're still in the main sequence, burning hydrogen at their cores. They haven't even started evolving yet. They're still burning hydrogen in the helium in the main sequence, but they are so hot and so large and so unstable, they just end up still in the main sequence, just shed. They don't need shells of hydrogen fusion. That core is generating enough to shed all that hydrogen away, and they become Wolf-Rayet stars while on the main sequence. They're the brightest out of the two classes. They're far brighter than your classical ones. You might say, they get up to 1 million times luminosity. And you might say, where does the nitrogen come from? You know, the W up here, the nitrogen, because, you know, they're on the main sequence. They haven't started creating heavy elements yet. They do have some, you know, from previous generations of stars, they're using the CNO cycle. They do have nitrogen in them, traces of nitrogen, and that brings itself up with convection to those outer layers. So let's have a look and name some Wolf-Rayet stars. So the Large Magellanic Cloud, that's a satellite galaxy, about 160,000 light years, beautifully visible in the southern skies. And it is home to the Tarantula Nebula. Most of you who are, do a lot of stargazing, you're probably very familiar with the Tarantula Nebula. If you haven't, look it up, get it through your telescope. It's just gorgeous. It's the largest star formation region in the entire local group of galaxies. Amazing. And it's some very large star clusters in there. And one of the most massive and luminous stars known sits up there in the Tarantula Nebula. So let's have a look. So here it is here. It's called R136A1. So one of the largest clusters in the Tarantula Nebula is called R136. That's the name they've given to it here. And I'll actually mention here, there's an interesting little correlation. The larger a star cluster is, the more likely you'll find the largest of your stars in there as well. There's a correlation between the size of the star cluster and the size of how massive they can get, the upper limit of their stars. Also, the most massive stars, and it follows with gravity, with a sort of gravitational sink, if you will, those more massive stars tend to be more in the central parts of the cluster. So there is a particular cluster, and here's some Hubble zooming in, Hubble images. Here's the Tarantula Nebula, and they're zooming in here on a nice big open cluster in the middle. And when they were finally able to sort all this out and resolve all these stars, they found a star in there which they called R136A1. They estimate it's somewhere possibly up to 300 solar masses. In theory, you should only be able to get up to 150, 200. And there's a thing called the Eddington limit where the radiation pressure is too much for gravity, pulling it together, and it should become totally unstable. But they think this one and others could be 250 to 300 solar masses. Surface temperature of 500 degrees. Luminosity, check that out, 4.7 million times the power output or brightness of our sun. And it's only 1.14 million years. So it's no surprise that's where it's sitting. That is the largest and probably one of the most brightest stars known. And what is it? It is a, I'm just going to go back here for a minute. I think I talk about that later. Yeah, that's actually a, yeah, I do it. Here it is, pardon me. Yeah, it's a WNH star. So it is one of these stars that are just so huge, so hot, so unstable, it's still on the main sequence, and just the energy from the core alone is just shed all the outer layer hydrogen away from it to expose sort of the core, if you will. And yeah, that's why that's an important class of stars. There's another one here in the Milky Way galaxy in Sagittarius. Here it is, WR, that's how you tend to classify them here, Wolf-Rayet stars. Look at this, there it is in the middle there, and look at all this big wind-driven nebula of just expelled ejecta or material around the outside here. That's also, no surprise, it's a WNH star. It's one of these really, that's all those massive, supermassive, powerful stars are WHN Wolf-Rayet stars. It's only one of about 500 that's been observed in the Milky Way, so that they are very rare. It's about 20,000 light years away, temperature 44,000, 12 times the radius of the Earth, and yeah, over 500,000 times as bright as the sun. So how about these luminous blue variables? Well, I spoke about the blue luminous variables, how less than 40 solar masses, reasonably stable, convert into, swell up into red supergiants. We then said above that 40 solar masses, you got mass coming off in a nice steady rate to create a Wolf-Rayet star. But you also can get these blue supergiants that just periodically, unpredictably throw out massive big upheavals, and they just biff out large amounts of material. And when you see that, you're looking, they call them a luminous blue variable. And here it is here on the Hertzsprung-Russell diagram. They're very similar luminosity to their other stars, but they're a lot cooler when they're going through these bursts. So massive, highly luminous, very unstable, and the variable stars, meaning they're variable, they're very unstable, so their brightness is increasing and decreasing. As I mentioned, unpredictable and quite dramatic. Also associated with these wind-driven nebulas here. So that's luminous blue variables. That's pretty much what I've mentioned here. The greater than 40 solar masses, it's the intermittent mass loss. Very short lifespans, less than 1 million years, and very, very rare. There's only been 20 of them identified so far. So very rare. Okay, so who can name, it's a well-known luminous blue variable, a clue, in the Carina Nebula? Eta Carina, absolutely. Eta Carina, and people talk about that a lot. There's that very bright star, point of light just right there. That's Eta Carina in the Carina Nebula. That's a common one you can often see, and you see in books and stuff. You can say, oh, that's a luminous blue variable. Let's have a bit of a closer look at it. And it's surrounded here by this big bipolar wind-driven nebula called the Homunculus Nebula. It's got 2 stars, and it's actually a binary system. The main star is a hypergiant, also known as that luminous blue variable, and the other one is an O-type dwarf, in other words, on the main sequence. The main star, it's about 100 solar masses, 4 million times as bright as the sun. It's less than 3 million years old, and its surface temperature, you might say, why that big fluctuation? Because remember, it's doing this, it's just having big outbursts and so on. So when it has an outburst, at its coolest, it's 9,500. When it shrinks back down again, it gets down to about 35,000 degrees. They saw that 1873. It was observed by astronomers. They called it the Great Eruption. They noticed the star sort of appeared to flare up, and it was associated with a big, massive outburst of material. It certainly brightened up significantly. So that's Eta Carina. That's a star that often gets talked about. You can see and so on. You say, well, that's a luminous blue variable, guys. I hope someone will be impressed. So hypergiants, yeah, that's a word you'll see here. They are just the biggest mass of all the massive stars, and they've evolved from the O-type dwarfs more than 40 solar masses, which makes them very unstable. Yeah, extremely large, low surface gravity, and just strong stellar winds with a lot of mass loss. Once again, very rare. Why are they rare? The IMF stands for not International Monetary Fund. It stands for initial mass function. In other words, that we talked about that pie diagram, how nature has a bias for more smaller amounts. So large stars are rare and very short lifespans. So that makes these big hypergiants really, really rare. Lifespans usually in the hundreds of thousands of years, up to a few million years. Very, very short lifespans. Some hypergiants, so we've talked about the most massive star that we've seen, up to 300 solar masses, that R136A1. So that's, do not be confused between massive and being large. These big hypergiants and red supergiants and red hypergiants, they are really large, but they're not necessarily high in mass. They're just low density because they've puffed up. But in particular, the largest one known to us is UY Scuti. And it sits here, and you're trying to find it. You think, oh, I might sort of show it to people. Yeah, its radius is at 1.1883 billion kilometres. If you put that in the middle of the solar system, it would almost reach out to the orbit of Saturn. That's 10 times the orbit of Earth. That's how large it is. Surface gravity. What's holding us on Earth? It's about, what, 9.8 metres per square second? You're talking 0.0032 metres per second. So the surface gravity is next to nothing, very unstable. Its parent magnitude, and I put that in here, 8 to 10, we visually see up to about 6. So that tells you it's not visible with the naked eye, but it's readily achievable with a basic telescope. M16, this is in the winter sky, our southern hemisphere winter sky, M17, Swan Nebula, Eagle Nebula, M16. They're very easily located when you're up stargazing. Here's Scutum, the constellation here, and UY Scutum just sits here. You should be able to see it, and you point that at the telescope, someone to look down and say, that is the largest star that we're aware of. It would go out to the orbit of Saturn. Surely they'll be impressed with you by then, if they're still hanging around. So there you go. So this is a series of flow diagrams that I've put together just to try and bring all this together. These are your 5 main types of massive stars. So they all start, of course, with a main sequence O or B, 0 to 1 or 2. Initial masses from about 8 to 10 up to 300 solar masses. So they always start there. The next stage is that they usually when they run out of hydrogen off the main sequence, they usually just gently puff out into these blue supergiants. Occasionally you get those WNH stars, the really, really, really hot ones, that will go straight to your Wolf-Rayet stars. So your blue hypergiants and supergiants, if they're less than 40 solar masses, they just gently puff out to red hypergiants and supergiants. If they more than that, they start losing mass. If it's continuous way, they end up as a classic Wolf-Rayet star. If it's episodic nature, they end up being luminous blue variables. They can also go directly to supernova or direct collapse. Let's just call it a supernova for now. That's a different talk, whether they go supernova or direct collapse, but essentially most of them end up as a supernova explosion. From there, your red supergiants, the ones with the large helium cores can go through that blue loop. They shed off outer material, heat up, stabilize, and then start to swell back out again, form a blue loop. And a blue loop is canopus, it's going through a blue loop. They can go directly supernova on their own, or they can shed their outer layers and go straight into a classic Wolf-Rayet star. The luminous blue variables, we got to those through I'm just getting this going. Luminous blue variables, we got to those through that sporadic loss, and when they go quiet or quiescent again, they sort of appear like a blue supergiant, slightly different. They sit on a slightly different part on a narrow strip of the Hertzsprung-Russell diagram. I've got this back again. Or it is possible they can just continue to shed mass and become a classic Wolf-Rayet star, or they can go supernova themselves. Then you've got your Wolf-Rayet stars, your Wolf-Rayet stars at the end, and of course they naturally end their lives as a supernova as well. So they all end their lives as a supernova explosion, as we talked about at the front. So hopefully that little series of flow diagrams has brought it all together for you, how they all interrelate. It's in the handout. It's a bit more complicated one in the handout, but it's all in there. So that's principles of massive stars, the different types of massive stars, how they evolve, and it's all driven by mass loss, open stars and associations. And that's how most of these massive stars are all found in these open star clusters and associations. And the reason being, as we've talked about, stars form from giant molecular clouds that start fragmenting up into smaller fragments, and they develop into stars. And of course, all these fragments here tend to be sticking together, and little groups of protostars, and the final stars they form are left in little groups. And there's two main types of groups. Open star clusters, that's where you typically get up to about 1,000 stars or so. They're all very young, because they're massive stars, only a few 100 million years old. They all formed at the same time from the same cloud. They're almost like siblings, if you will, brothers and sisters. And they're all gravitationally bound still. But eventually, over a few million years, they do disperse and go their own way. And as I've mentioned, this is the jewel box, by the way. If you haven't seen that stargaze, and that's got to be high on your list to look at things, it is just absolutely gorgeous. Stars of all different temperatures. So you see emeralds and rubies in there and all sorts. Do yourself a favour if you haven't seen it and get a telescope. You can even see it through a good pair of binoculars. I've mentioned here the correlation that the larger stars are more likely to be found in larger clusters, and it's the centre of those clusters where you'll see the most large, or the most massive of those stars. So how about associations? I've got my head around clusters. In most textbooks will talk about star clusters, but you kept reading about OB associations, and it took me a while. What are OB associations? Well, essentially, in a nutshell, they're just younger, looser, and smaller versions of an open cluster. So you've typically only got 10 to 100 stars. They're much younger than open stars, so there's less of them. They did form it all at the same region, same time, so they're still siblings, but they're not really gravitationally bound. They're just very, very loosely together. They just happen to be traveling through space sort of as a group together, but there's not much gravity to speak of that's really holding them together, and they disperse very, very quickly. Usually by the time that they've blown away all the dust and gas scraps around them. They've started to wander on their way. So in a nutshell, they're a younger, looser and smaller version of an open cluster. That's all they are. Often you'll see books and papers, oh, we're looking at such and such OB cluster. That's what it's about. Or OB association rather, I should say, sorry. Okay, so let's wrap up what we talked about tonight. So we talked about 6 principles of massive stars. We said they were rare due to the initial mass function. Nature's got a bias to having more smaller stars and much less larger stars. Remember, just those O and B stars make up less than 1% of all stars on the main sequence. They're also very short-lived because they burn through their fuel so quickly. So they're short-lived, that sort of adds to their rareness. They're very bright. Why? Because they're hot and they're very large. And those are the 2 factors, your temperature and your size, that dictate your luminosity or your brightness. Types, there's different types of massive stars. And really the bottom line is they're characterized by swelling and instability associated with mass loss. Why? They're big, so they're hot, huge temperatures going on in the middle, you've got convection going on, then radiation going on, so this low surface gravity, a lot of fierce stellar winds, they're losing mass, and the smaller ones, the relatively small ones that are reasonably stable, they continue to swell. So those are your 2 main factors that are driving their evolution. And they typically found in open star clusters in associations in regions of star formation. Why they are then regions of star formation, and I put that up right by one of my first slides, is because they don't live very long. They haven't got time to wander off anywhere before they go supernova. And as I've mentioned there. So, that is part 1, Home to Massive Stars, Introduction to Massive Stars of the Galaxy. Hope you've enjoyed it. Thank you very much for your attention. Thank you. Now we'll take any questions either from here or online, Steve, and if you online you want a copy of the handout, just send me an email, membership@astronomy.org.nz, and I'll flick you a PDF file of that. Or if you came late and you haven't got one, you're welcome to grab one just here. Any questions? Oh, Niven.
These massive stars which have such short lifetimes, where does the gas come from? Because you talk about that, as they evolve, these clusters disperse. Why wouldn't it be over the lifespan of the universe, just not enough regions of that much gas to form these massive stars?
It's just from previous generations, because the previous generation was such short-lived too. Just previous generations.
I mean, I get that, the matter's still there.
Yeah. Yeah.
Well, it's tied up in the remnant or the black hole or whatever, so it's sort of this diminishing return and dispersion of the matter.
Eventually it does all go, and you get sort of young, active galaxies. I wouldn't call the Milky Way active, young, but it's sort of active, full of star formation. And there is enough gas and dust there. Eventually, they do run out. Galaxies run out of gas and dust, and that's elliptical galaxies are dead. There's just no star formation going in. They have run out, and they look red because old stars are red giants and supergiants and stuff, and they do run out. And we're just in the Milky Way, surrounded by, the large Magellanic, small Magellanic Cloud. We can see it's got a lot of gas and dust. They're obviously relatively small young galaxies. Andromeda Spiral, Triangulum Galaxy Spiral. We're just lucky that in our local group. But yeah, there are elliptical galaxies out there that have run out and that are dead. Dead in the water, yeah. Now, a question that sometimes comes up that you'll read about too is they talk about the red supergiant problem. What is the solution to that? And that refers to when they look at a supernova, they then go back through their archive, through the previous, sort of looking for a better word, plates or images of that region of the sky, and they try to locate the progenitor, the original star that would have gone supernova. And they analyse those images, and they concluded that supernova type 2P, that's a type of supernova, and we'll talk about, I've got a whole talk next year on supernova explosions. Type 2P, it's a particular type of supernova that's rich in hydrogen in its spectra. None of those type 2P supernovas had red supergiants greater than about 15, 17 solar masses. It was a real problem. And the solution is twofold. One is that probably those higher mass red supergiants have actually evolved and shedded away a lot of mass, so they've become luminous blue variables or Wolf Riot stars, or they've just lost sufficient mass. There is another type 2 supernova called type 2L, and it all depends on the light curve, instead of it's linear instead of P for plateau. And the linear referring to it's going straight down, it's got much, much less hydrogen. It's got hydrogen there, so it's class 2, but much less. So they could be type 2Ls. But the other thing is, because the bigger they are, the more obscured with these stellar winds, a lot of dust and stuff. So maybe they're underestimating, because of all the obscuring of the dust and gas and dust around them, they're underestimating their size. So they actually are there, they are bigger than they appear to be. Remember Beetlejuice a year or two ago, it was in the news, oh, it's looking all dodgy, it's going to go supernova any time now, hide under your table. You know, they concluded at the end of it was just a big fizz, it was just, they concluded it was probably just a lot of dust and gas sort of just obscuring it, and it looked a bit funny from that. So I throw that in there because that's a question that sometimes people have. What's the red supergiant problem? That's what it is, and those are your two solutions for it. Yeah, Robert.
You showed us a pie chart earlier on.
Yes.
Of the
initial mass function. Yes.
Well, the ratios of the different size stars.
Yes.
Has that been consistent, do we think, from the start of the, you know, from the Big Bang, the amount of large stars ratio-wise to the smaller stars? And on that as well, do the larger stars take less time to form than the smaller stars?
Yep. Two good questions there. So we can't see the first stars, that's what the James Webb's looking at. So that is applicable to the Milky Way galaxy with its set metallicity. Whether that differs slightly, I've never heard, because that's sort of a basic principle of astronomy, where it differs slightly through perhaps a galaxy with slightly different metallicities, like the Andromeda galaxy. I don't know, but if it would, I haven't read anything to that effect. My understanding is certainly for most generation, you know, your population, one population of stars, that probably is consistent. That nature just has a bias for small, and you're probably getting it. How about those exact percentages? You know, is it a little bit off from there? It could be, I don't know, but I think the principle stands that nature has a bias. And I remember when I started reading about that, I thought, oh, it's like a pyramid then, like that. Oh no, it's not like a pyramid. It just, as you saw those figures, it just goes like up like a tall peak. You know, those O stars are less than 0.000013% versus the M class stars were 76%. Huge difference. Whereby your red dwarfs, which are your K and your M main sequence stars, they make up, oh gosh, you know, something like close to 80-90% of all main sequence stars are red dwarfs. So the principle's there. Whether it differs from populations of stars, I'm unsure. May do. I'm unsure, but I think the principle is the same. Now, what was your second question? Was
the larger stars take less time to?
Do the larger stars take less time to go through that process? Yeah, they lead very short lives, but they get born, looking for a better word, they get up and running a lot quicker. Whereby those nebula, you see those emission nebulas like M42 and the likes, that's all from those big initial OB stars that are up and running early, and they're blazing out ultraviolet light, which is fluorescing all the hydrogen around it, ionizing and fluorescing the hydrogen around them. And a lot of those star clusters, the medium and the small stars haven't even got going yet. As you see that, you know, you see in those like the pillars of creation and the Carina Nebula images, they're still shrouded in dust and gas as protostars, and the big O and Bs are up and running, just blasting out ultraviolet light everywhere. So usually when you get to a star cluster, the star clusters you see with those like R136 and so on, with those big massive stars, they're really, really young clusters. When you get your reasonably mature open star cluster that hasn't yet dispersed, but it's reasonably mature, you've got some, you know, some red dwarfs or some Ks and G stars in there. The big OBs have long left. They've been and gone. They're long left the scene by the time the medium-sized stars sort of arise. So I hope that answers the question. Any others? Yes.
Can main sequence star types only become white dwarfs?
Yes. Yes. So the question is, can some of those OBs And I actually had it up here earlier and I took it out with when I was finally doing the slides before I came. I thought I don't want to go there. But yeah, you've picked it up from the diagram in there that yes, they can. Some of the big massive O stars that go to those WNH Riot stars, while they're still in the main sequence, they're so ferocious, they shed so much of the outer layers off, they leave an exposed core, and you're starting to get a bit of carbon and oxygen getting produced in there, and they look like white dwarfs. So yes, Riot stars, and via the OB, so it's the WNH of the main sequence becoming a Riot, can then morph into what looks like a white dwarf. Yes, very, very rare. But yes, it has been documented, and in theory it can happen. It has been documented. Yeah, good question. Steve, any online? No, covered it all. All right, guys. Now I just have one more slide there. What have we got next year? So we're going to have our annual quiz next year. It'll be covering all your material. It's fun. Don't feel too threatened by it, so it's just a lot of fun. It's more of a learning point. We have a question, multi-choice, hands up, who said A, who said B. It's pretty relaxed. We have a giggle. Someone gets some chocolate out of it, and then we talk about some talking points. Just an excuse to have little talking points about each topic. And then it'll be March, we'll do regions of star formation too. We're going to talk about the infant stars. You know, what's the difference between a protostar and a pre-main sequence star? We're going to talk about that sort of stuff. What's going inside these stars, convection-wise? What's a T Tauri star? What's a Herbig object? Herbig-Haro object? All these terms that you think, whoa, I vaguely recall people talking about these. We're going to, just like we talked about luminous blue variables and Riot stars today, we're going to bring up some terminology and make it simple for infant stars. So we're going to do that, and then the rest of the year will follow, and we'll have loads of fun. So from the introduction to astronomy, I know it's not the end of the year for the society, but certainly from the introduction to astronomy, it's the last one for the year. So hope you have a nice, safe journey home, and followed by a lovely Christmas and New Year. Thanks, guys. Thanks very much for your support. Thank you.